In order to get this AY-3-8910 programmable sound generator chip up and running with Arduino Nano, I had to do some research to figure out what features this chip even has and how to use it. Even though I'm using an existing Arduino library, I still needed to do some research. So this chip was made by General Instrument back in the late 70s, and it was designed with interfacing of one or two specific chips in mind, so that partly explains some of the interface pins on here. For example, in the datasheet, there's mention of these 3 bus control pins, which control when you want to access a register to control this device or read from it. It seems like this setup was intended for one of these specific chips, but now if we're using an Arduino, we can simplify it down and only use 2 of these pins and tie the other one just to VCC so that bit is always high, and we can still control and interface with the chip. So that's this CP1610 chip right here that it was, according to this article, initially going to be used with. Otherwise, this sound generator was used in old arcade games. For example, Gyrus had 5 of these chips, so I guess that gives it up to 15 different audio channels where you can make music with more than one note playing at a time, as well as a bunch of percussion and sound effects. And it was used in all kinds of old home game consoles and small computers. But looking at the capabilities and features, it has 3 tone generators that you can turn on at once. There's a single noise generator, which is a pseudo-random white noise generator, and you can switch that one generator in and out of these other 3 channels. You can control the volume of the 3 channels, whatever you happen to be playing through it, and you can use an envelope generator to control the volume. So instead of just setting the volume at a certain level, you can make it fade in or fade out or do a few other things. So if you're making white noise, for example, if you fade it in and then fade it out, it could sound sort of like rolling waves or something. And the tones generated are square waves. So by accessing the registers of this chip and setting values in the registers, you're turning on or off one of the 3 sound channels, whether or not it's playing a tone or if it has noise, what the pitch of the noise as well as the tone will be, what the volume level is, or if you're using the envelope generator to automatically do things with the volume. And we'll look at some of that in the datasheet. Beyond that, there were different versions of this chip, including Yamaha had licensing to make their own version. So these chips, or certain variations of them, were used in all kinds of things back in the late 70s and early 80s, essentially providing some sort of a sound card type interface. The datasheet I found is 55 pages, so if we just kind of skim through looking for anything that can tell us how to use this, there's one typical application circuit using that original targeted processor, those 3 bus control pins, and here's the address or data 8 bits. So by using these bus control pins, we tell the sound generator we want to access a certain address with 8 bits we give it. Then we latch that in, and we control it to now read or send data to that register address. Then the chip will just turn on or off a tone or noise or change something about it. The 3 audio channels have their own output pins, and in the typical circuit, which is also what I used, they all get combined as a single mono audio channel. And in all cases, I've seen this 1K resistor to ground required. I'm not sure exactly what that's doing or if it's described in here somewhere. And then there's some other stuff. Mine is a little different than this. There's another circuit in this datasheet, we'll see. So in this case, I'm using an Arduino Nano to control these bus control pins, the 8 bits of address and data, and resetting of the chip, as well as the Nano is generating a 2 megahertz clock using the built-in timer to just automatically generate a square wave out at 2 megahertz to run this chip. And I did find it necessary to connect the reset pins so we can control it, because when I was experimenting with this, Originally, I was not using reset, I just kept it active all the time, and the tones would play, but when I tried to generate noise, it was just barely clicking, it wasn't working. I thought the chip was broke, but after trial and error, as soon as I reset this chip pin, the noise channel started working. So I made sure I connected this to the Nano so I can always reset this when I'm initializing after power up. And we're not going to deep dive into exactly how to use all the bits in all of these registers. We just need to know that there are 16 of them that ultimately control the whole chip. So inside this chip, when we start using these bus control pins and telling this that we want to read or write from a certain register address with certain data, by putting various data bits into each of these 16 registers, we're controlling things like the tone of 3 tone generators, the pitch of the noise, and we can turn on or off these audio channels, control their volume, or control if they're automatically having their volume changed with this envelope, and what kind of envelope are we actually doing to control the volume. So one of the things that confused me with trying to figure out in a Nano, how do I tell this which register I want? We know there's 16 registers. This goes from R0 to R17, and here it skips from R7 to R10. So I realized later, this is in octal as opposed to decimal or hex. So really this goes decimal 0 to 15, but the Arduino library takes care of that anyway, so it's just a weird thing. I'm not used to dealing with octal. And on this 40-pin chip, there's a few other things, like 2 more 8-bit I/O ports. We're not using that here, and it's only optional as far as being able to use all the features in the chip anyway, so we're just going to skip all of those kind of things. So later in the datasheet, it gives a couple of examples of how to control those registers by putting different octal data values in, and that's where I got the clue that maybe this is in octal as well. So to make what they're calling a gunshot sound effect, I still don't understand this. Any not specified register, setting it to 0 as the first step in both cases. I don't know what that means, but aside from that, register 6, if we send certain data to register 6, it will set the noise period about halfway of its range of values. So register 6 is the noise period, and you can set 5 bits. I think in hex the maximum value is 1F, I'm not sure. So basically this period, 1 over period, is frequency. So what you're really doing is setting the pitch of the noise. You can make it sound low pitch and more dull, or higher pitch, more like a hiss. So we set that up toward making a gunshot sound. Then we have to actually turn on the audio. So in register 7, we enable noise and not tones on all 3 of these channels. So that's the enable register, and we're going to enable noise and not enable tones, which would be configured up here. Then in the rest of these registers, we're dealing with setting up the amplitude control with the envelope generator to change the volume of this noise. So we set something to go for about half a second, and it's a decay envelope with 1 cycle. So I guess it goes with a burst of noise that will gradually get quieter. So that's the approach used for doing different things in this chip. And I didn't set it up to do that, but I did set up a few more things between noises or actual tones in a demo sketch we'll get to. But let's say we wanted to play a tone on channel A. We would just simply set 2 data values here to give a total of 12 bits that essentially give us a certain audio frequency. Then we come down and enable at least channel A tone playback. And we're going to want to set the channel A amplitude either with these 4 bits to give us a certain fixed volume level, or this M, I forget what M stands for, maybe modulated amplitude. So that's where we turn on the envelope generator, so the sound is going to have its volume changing. And that is based on all this envelope stuff here. Do we want it to fade in or out, and how fast, and things like that. So that's essentially what this chip does, and what the Nano is going to have to do to access a register and set the data to achieve the result. And the library I'm using is this one. So I had to download the zip file from this main GitHub area to get the library files, and then I manually installed this in the Arduino IDE. So there's all kinds of things going on here. And if we just start out by actually glancing at the library itself, one of these files contains basically a table that we can access with data that we would put in the sound generator for one of the tone channels, and it corresponds to certain musical notes. I think this is C and C sharp, for example, and it's just those kind of intervals here in different octaves. So octave 0 is the lowest octave. So we're setting up the period value in the chip, which corresponds to a frequency, whether it's a low tone or a high tone. So we can use this to just try and quickly generate a melody. In the register definitions, this is just how we can use some shortcuts here. When we're trying to access a register, we can do things to say we want to control certain things within a register, like turn on or off noise or tones within this single enable register. We have all the tone, all the noise, and so on. So this section deals with the enable register, and just looking at the code examples, we can see how these are used to more easily figure out how to control the register. Same thing with the envelope control. We just kind of use these legible labels to try and control the register a lot more intuitively. And then looking at the examples, for simple tones, first we have to do some obvious mandatory setup stuff. So we declare what pins on our Nano are used for the 8 bits of data and address control, and those 3 bus control pins. But there's another way to initialize this, actually using more pins, including the reset that I figured out I needed to use. So we'll look at that in my sketch. Otherwise, using the Uno or Nano 328P chip, we can use that to set up this 2 megahertz. Well, this demo is using 1 megahertz, but I'm using 2 megahertz automatically generated clock on a certain output pin, and that's on pin 9. So this is just setting up the timer to automatically generate whatever frequency we're doing on this pin. And then we just go and do the rest of our sketch, and we're not stuck managing the timing of generating a constant clock. So now in here, they're just playing some simple notes using those shortcuts here to set the frequency that gives us a G or an E in certain octaves. So after initializing everything, this sketch just goes to the programmable sound generator and sets a certain amplitude on 2 of these tone generators. One of them is going to be lower volume than the other. And then accessing the enable register, the channel A and B tones are turned on, but not noise or anything else on channel C. So this is the approach to manually setting up this tone generator. And then it goes through a loop and just plays this sequence of tones right here for a simple melody, and then just ends the sketch. So using this, I then just kind of went on and figured out how to get the noise to work, and then I made my own demo that we'll see. But the other example they have, chiptunes, which is basically old 8-bit audio, just like these old video games or computers made. This can play files from an SD card, which I did set up. So in this demo, the SD card is being used. The SPI needs a chip select, so it's on a certain pin. Again, we're generating this clock, and this time it's at 2 megahertz. And then there's just basically SD card access. So it goes in and looks for all the files on the SD card, which are YM sound data files. And it will just go and get the data out of the files and send it to the sound generator chip, playing them one at a time until it's done. Going back to the main page on this library, it is basically a chiptunes player for this chip. In order to play the YM chiptunes audio files, there's a README page. So the first thing you need to do is get some of these YM audio files, and it gives some locations here. And I went to these and settled on a certain one, which is this miscellaneous demos on this other GitHub area. So the reason I went with this is trying to be YouTube friendly. Not that I know what any of these are from, and if any of this might be not something you want to play publicly for certain reasons. I just went with it. So I took a few of these YM files. Basically, you just click on one, and then you can just click to download and save it somewhere. And once you have the YM file, it's basically a compressed file with the old LHA format. So we need to decompress it, and right now I'm on a Mac, so I had to figure out, I can't even remember how I did it, I had to install a command line LHA extractor. So I downloaded a bunch of those onto this USB drive that I'm doing some other stuff with. And if I'm going to say that I'm looking to work with this text intro 1 YM file I just downloaded, on my command line after LHA is installed, I extract that file name, so I can do that. So now it extracted this new YM file. Sometimes it'll be a .bin file, so you just kind of have to pay attention here at what new file shows up. So now that I know this was extracted, we go back to those instructions, and step 3, to make a long story short, I'm using method 2. So I went to this place here and downloaded decoder.py, the Python script, and you basically have to run it on the file name that you just extracted. So I've got that decoder.py right here, and there's the script that will run. So now I'm running Python using this script, and I want to take this file that was just extracted from the main one and forced interleave to set it up the way we actually need. And now it's going and seeing all this command control data that it's going to send to the sound chip. And once it's finally done, it always just creates something called output file with no extension. So I just rename it. So in this case, let's just call it text intro, and I'm just going to give it SNG for song, or I could SND for sound. It really doesn't matter in this case because the sketch will just open whatever file it is and it will assume it's a proper file as we just made, so it can be called anything. So basically that would get copied along with any other files I made over to the SD card and plugged into that Nano. So there's a lot of little details. That's why I'm making this extra longer video to show all the steps, but it all comes from this library GitHub location where the steps to do this for the SD card are in this little note here. That's where I started from and got it working. And here is a quick view of the schematic I am working with. There's the Nano, and the SPI bus, including this chip select pin, goes to this connector here. And this is intended for one of those micro SD modules that have a built-in 3.3 volt level shifter, so it can work with 5 volts. And you can give it 5 volts, and it regulates down to 3.3 to run the SD card. Then we just have all the other control and data pins that go to this sound generator chip. And the 3 audio outputs are set up very similar to that datasheet recommended circuit. Here's the circuit from the datasheet. So they're tying the 3 outputs together with the 1K to ground. Then there's a series resistor and a shunt resistor, which I believe is controlling the amplitude of this so it's not too loud. And also we have this capacitor here, so we have a low pass filter. Especially with this being square wave generated audio, we want to limit our upper frequencies here, so we're just really getting the audio that we intend. Then we have a series DC block capacitor to send audio out. That's essentially what I'm doing here, although I ended up with this resistor way over here. I think I had seen some other reference circuits set up more like this. And maybe this could be considered an advantage in some cases because it helps give a ground reference when plugging in some other audio instead of this capacitor directly blocking DC. Maybe that's not always desirable, but it seems okay for what I'm doing. And finally, over in my demo sketch, which is heavily based on the library we were just looking at, so I'm setting it up to be able to play files from the SD card. And I'm using, as I mentioned, this more extensive sound chip interface, including the reset pin that I found I do need to use, or else I can't get the noise generator working. So after everything is set up, here I'm generating that 2 megahertz clock for the chip. And here, this is the generated 2 megahertz clock. I put a 75 ohm resistor in series as a terminator so that it might help signal integrity if we have signal reflections on this line. I've seen some circuits using 100 ohms here. I figured whether it's needed or not, if I don't need it, I can just put a jumper wire across here. So when I put this on the scope, I did see my 2 megahertz clock, and then I tried putting a jumper wire momentarily across the resistor to just create a single solid connection instead of having a terminating resistor. And basically the signal looks very similar. If anything, I might see a slightly reduced amplitude when the resistor is in circuit, but I think it would have worked either way. And then in the setup section here, after doing all the mandatory stuff, I call this function here to play some demo sounds, which is a few tones and some noise, just so I could learn how to use this thing. And then my main loop is basically the SD player for those YM files straight from the other library demo sketch. So basically it's going to power up one time, play these demo sounds, and then just go do the SD player. So what I'm doing here, using the library commands after I figured out how, I'm just, for example, making sure I start out by turning off all the tones. So in the enable register, I turn off the tones on channel A, B, and C, and then I start out only wanting a tone on channel A, so I turn that one back on at a certain volume. Then, using those shortcut note references, I'm playing a C note from their arbitrary third octave frequency. So since this is, I believe, a 12-bit data configuration in these two registers, we have to send the data out in two commands to get to the two different registers, coarse and fine. So I'm playing this C note for half a second. Then on that same channel, I switch to playing, I think, D sharp for half a second. Then I want to keep that final D sharp playing, but I'm going to turn on another audio channel. So I'm going to start playing another tone along with it on channel B. And that's going to be an F sharp for half a second, and so on. So I'm just going through, and I end up eventually with notes on A, B, and C being switched on and off. Then I'm done with the tones, so I turn off the tone channels, set those volumes to nothing. So here's a quick scope waveform of some audio playing back, where we can see all the different square waves on the different audio channels, different frequencies, all combining to this final audio signal. And now I want to start generating noise. So first I want to set up a lower pitched noise, and I want it to fade in. So I enable the noise. I set the pitch that I want. I think this 1F is the maximum number, which gives us the lowest pitched noise. Then I turn on a certain envelope to control the attack, which is the initial part of the sound. So it's going to fade in at this certain rate, this pitch of noise. And I have to set the amplitude on the channels using this with the 1 here in order to enable the envelope itself instead of directly setting a fixed volume level. Right here, those amplitude registers, this is where the 1 gets set for the M, and that turns on the envelope control instead of these 4 bits here for the fixed volume level. So then I set the noise to have a higher pitch, and I want it to fade out in volume. So I set up a different type of envelope. I don't really understand what all these envelope words mean, so I just kind of put in notes what seems to have happened. So this configuration here made the noise at a higher pitch fade out instead of fade in with volume. Then I set this continue envelope with a certain noise pitch, and it kind of kept repeating like a quick sound, like maybe a clap or the sound of a video game character in the old days just kind of walking, or if you're tapping on a metal object. I was getting that kind of effect. And then I made this lower pitch noise again using a different envelope again, and it sounded to me like an explosion. So that's what I called that. Then I just wanted to turn on noise at constant volume just to hear it, so I did that. And that's basically the little custom demo I made, and then it goes into playing those YM audio files. So if we let the sketch run, here's how the little demo notes and the noise sound that I created, followed by some random snippets of some of those downloaded YM song files.